we left it at this point yesterday. This polynomial P was defined, which is we know since Q1, Q2 differ on at most t locations with a fixed string. So this polynomial is 0 on at least k minus 2t locations. And that gives us, if we choose k equals m plus 2t, it will guarantee that there will only be a unique polynomial within t errors of the received string. Okay. So from this, now let's try to see what is the size blow up that happens. So we started with n bits, if you remember, and this in this algorithm what we did was that we chose, if you remember, m such that m is n by l. L is the length of each aj. We chopped the message into L bit blocks. Okay, and k was the number of points on which we evaluate the polynomial q, which is of degree m minus 1. So let's just put it all together. Continuing from there, m is n by l plus 2t. T is the number of errors we wish to tolerate, and this tells us the number of points k on which we need to evaluate. Now this is dependent on two parameters, one is L and one is k. K, if the number of points on which we evaluate the polynomial is k and we concatenate all the evaluations, what is going to be the resulting size of the string that we get? Look at this. This is the polynomial q. We evaluate this polynomial on alpha j's and we get pi, which is q of alpha I, and then concatenate all the b's. What is the size of this output? It is about k times the size of each bi. Of course, different bi's may have different size, but if assuming that they are about approximately the same, so an approximate estimate would be k times the size of bi. So what is the size of bi? Well, it depends really on the field on which we are working. So let's say we are working, let's say to begin with integers. That's the most natural starting point, that each ai I treat as an integer between 0 and 2 to the l minus 1, and then evaluate this polynomial and then see what is the result we get. So what is going to be the size of the number bi when you evaluate polynomial q on alpha I? It's a degree m minus 1 polynomial. Sorry?
Maximum of all alpha is?
Yeah, let's say maximum of alpha I. Yes. In fact, since we have to choose k alpha I, it could simply be 1 to k. Right? We could have done with any k alpha I. So maximum is k of alpha I. Then look at this polynomial. So for x, we will replace at the max k. So we will get k to the m minus 1 here, multiplied with a m minus 1. This will be the biggest number. All the other numbers will be smaller. So if you just stay with this, the magnitude of this number, a m minus 1, has magnitude about 2 to the l. Okay, and so this will have magnitude about k to the m minus 1. So overall magnitude would be, you can say bi is roughly 2 to the l plus m log k. So that means how many bits will each bi require? L plus m log k bits. So the total size, even if we ignore log k factor, let's say L plus m bits. So total size here would be k times L plus m. That many bits would be needed. In fact, there will be more bits needed, but this is a very conservative estimate of the bits required. And the value of k we derived from here was this. So, if we use integers, size of output is n by L plus 2t times L plus n by L. Okay, and this is n plus 2tl plus n square by L square plus 2tn by L. So this is the output size. And if you notice, typically we want L to be a small. We don't want to deal with two big numbers. So the dominant term in all of this is going to be this n square by L square. Because t is also comparatively much smaller than n. L is comparatively much smaller than n. So n square by L square is the dominant term. So which tells us that for starting with n bit of data, we have to roughly go to about n square bits of data in order to recover from t bits of error. This is an improvement from, well, not depending on what the value of t is. This may or may not be improvement on the trivial scheme. There it was about 2tn. Here it's about n square. It really depends on the value of t that this may be better, this may even be worse than the previous scheme. So it doesn't seem to be gaining us much until we realize or notice that all of this calculations we did could have been done over any field. There was no necessary, it was not necessary to do it over integers or rationals. And the problem with all this that arises over integers is that the size of these b's becomes humongous, very large. We started, the a's are L bit long, and suddenly we see b's become L plus m bit long. So there is a whole value m gets added, which is a pretty large number. And b's arise as a result of arithmetic operations over a's. So do you know a way of keeping the size of b limited? That is, can we choose a field of operations so that the b's will also have small size? Yes. Different values. The field should be large, Yes, but that is certainly true. My question is, can we reduce the size of BS so that the output size is small? When we choose everything over integers or rationals, so when you talk about the field, the size is blowing up. Exactly. Do it over finite field, because no matter how much arithmetic you do over FP, you stay within FP. And the size of an element of FP is only log p bits long. In fact, going back to the particular finite field I earlier talked about, it very naturally fits in here. We choose each AI is L bit long. So we treat AIs in F2 to the L. And everything, now these will also be in F2 to the L. But here the important point is that we need k distinct alphas. So 2 to the L must be at least k. That's important. So L can't be chosen very small. We have to choose L slightly large enough so that it is at least k. And now, what is the size of B when we do this evaluation? Well, BI is also in F2 to the L. So it's just an L bit long number. So instead of this, we now get this to be exactly equal to k times L bits. Each bi is L bit long, k of them, k times L bits. So now let's go to this side again. Let me just start from here again and do a calculation. Size of output is k times L, and that is L times n by L plus 2t, which is n plus 2tl. Now we get something very significant. This is telling us n is the size of input, size of output is n plus 2tl. Just an additive part. And notice that n is going to be very large, in the order of gigabytes when you talk about storing in a DVD. T is, I said maybe 1 meg, I took this to example, right? Maybe 1 MB for T, if you remember. 1 MB, right? I picked number of words to be 1 MB. Yeah. So about 1 megabits here, and L is the choice of L is ours. So we choose it to be small enough to take in k values. Okay, so that it won't be very large. So overall, if you see the addition in here, it's going to be much smaller compared to n, and that's what gives us a real error correction with very little overhead. Ideally, the overhead was, again I mentioned here, n plus t. Start with n, and n plus t is the increase in, t is the increase in size. Here I am getting n plus 2t times L, so it's not quite the best. But it comes very close to being best, especially for CDs, DVDs, because if you, the kind of error that occur there is scratch. It won't erase a bit. A scratch is, if you amplify it, it is many bits long, win width. So we'll basically remove large number of contiguous bits. Okay. Now if you store each element here in L contiguous bits, so when we remove a bunch of contiguous bits and say t bits contiguous in the extreme case, it basically means we are removing t by L elements. And so this L factor of L will go away. So the loss is simply n plus 2t in that case. It's a rough argument that I am giving, but it does come down to very small. And that's why the code that I described is variation of it is the one that is used to store the data on CDs and DVDs, because it gives excellent performance with very little additional space required for correcting errors. Okay. How did this become possible? Finite fields. If finite fields were not there, it would just not be possible. In fact, all communications, this is the code that I described is used for storage in DVDs, CDs, but for communication over microwave, radio waves, a variation of this algorithm is used, but that also critically uses finite fields. In fact, just about any error correction algorithm uses finite fields, and for the same reason. Otherwise, the size after doing arithmetic keeps blowing up. So although seemingly innocuous and also seemingly very abstract entities, finite fields are at the heart of modern life, I would say. simply modern life will not be possible. No, none of phones or because if you don't have error correction, if you call somebody, you won't be able to hear what the other side is saying. No data storage will be possible proper. There will be very easily, there will be errors in the data. Communication, internet won't exist. Nothing will exist. And we arrived at finite field just by this pure abstract algebra. We said, let's abstract out right in the beginning the heart of or the key operations or concepts of arithmetic and see whether we can generalize it. We generalize it and we said, okay, here are rings, quotient rings, fields, and then we found there are a whole bunch of kind of fields. Some of them are extremely useful, finite fields. So I hope this convinces you that the algebra, as we study it, is really fundamental, and it required this process of abstraction can lead to unexpected benefits. Okay. So this ends this one example. I'll end with very quickly of describing another example, which again something I promised probably in the first class, geometry. So far most of this course has been spent on looking at arithmetic, numbers. See in what way can we study numbers by generalizing it and abstracting it out. The other fundamental objects of study in mathematics are geometric objects, curves, surfaces, and you would like to study them also. Studying them is more difficult than studying numbers. The numbers have very nice structure. We have already identified a lot of excellent structure, and we can use this. A lot of tools have been developed to analyze them and work with them. Some of simple ones I gave you a glimpse of this. On the other hand, geometric objects have a problem that you first have to visualize them. When you want to talk about a circle, you have this picture in mind. There is a circle, and then you have a tangent and trying to do something. With simple geometric objects or curves, it is fine. But anytime you go a little more complex object, let's say a high order curve, or even a circle over complex numbers, can you visualize it? X square plus y square equals 1, where x and y are complex numbers. You can't, because it's no longer a two-dimensional object. In fact, there is if you look at this curve, this also came up somewhere in one of the analyses, right? -2. And see, in order to solve for this, we had to go to not just integers, but we had to extend the ring of integers to this algebraic integers and argue over that. I mean, there is a complex number also that came in there, right? Some part of I was a square root of -2. Did we have square root of -2 thing, right? So there is some complex numbers also come in. So we are actually looking at this curve, this will over complex numbers. But now we didn't use geometry at all. We just simply used the basic numbers or arithmetic to derive the solution that we want. But that was we found only one solution. Right, we gave one solution and we can say that other solutions cannot exist. But curves like this, for this specific curve we can do it, but in general of this curves of this kind, if you want to analyze, we are not always able to do or solve it as simply as we can do it for this curve. So there it becomes important to analyze the geometry of this curve. But how do you analyze geometry of this curve when it is over complex numbers? Over reals, how does this curve look like? When x cube is between 2 or negative, in fact, x less than cube root of 2, it doesn't have any solution. And x above cube root of 2, it will have solution. So it will look something like this, I think. Something like it's symmetric around x axis because there is a y square term here, and then it will look something like this. That's our reals. How does it look like over complex numbers? It's hard to even imagine. Now, with some more advanced analysis, we can figure out what it looks like over complex numbers, but it is nothing that you would imagine. This looks like a donut. Or tire. So it's not a two-dimensional object anymore, it's a three-dimensional object, because now we have complex numbers, so it's there are 4 independent variables in the complex number, because there are y and x both are complex. So the shape of this curve is like donut. It is 3-dimensional because one dimension is cancelled by the equation. You see, this is 2-dimension equation, but there is equation, so it eventually becomes a single-dimensional object. So when you have 4 terms and there is an equation set up, and there are 2 equations set up, real part and complex part. So that reduces the dimension. It becomes a 2-dimensional object, but it is rendered in a 3-dimension space. Just like this is a single-dimension object, but rendered in a 2-dimensional space. That is totally unexpected. There is really no way you can make a guess that it would look like this. So the question therefore is, how do we study the geometry of such curves? Imagination just gives up, not possible. And there again, the algebra that we have developed comes to our help. So let's look at a simple curve, which I'll just use an example. Maybe the simplest possible. A circle. This is a nice, over reals you can visualize it, but over complex numbers, like I said, hard to visualize. What I'm going to do is abstract out all the geometric properties in an algebraic object. Okay. So let's start building up this. It is called a dictionary between geometry and algebra. So what are geometric things? Curves, points, tangents. These are geometric entities, and we'll build a corresponding concepts on the algebra side. So first, it's a simple 2-dimensional space that we are working on. So let's first build that, the base. And it will be useful to start with an algebraically closed field, so we'll just stay with complex numbers. The space, 2-dimensional space over complex numbers. That's where these curves exist. This is not too difficult. This is something we already have been doing. We have been studying geometric objects like circles with algebraic equations like this. And this curve is simply a polynomial which lies in this ring, right? This is all polynomials in x and y, which correspond to all curves over C square, 2-dimensional space. So that's a simple correspondence. And in the school, this is where we stopped, right? And there is a little bit more. But let's go beyond. Points. a point in C square. What does it look like? Valuation, no, we'll just stay in this ring. I just want to, just like this is the space encompassing everything, all objects we are interested in. Similarly, this is now the ring where everything that we want should be there. So this contains point, constant polynomial. Okay, what constant polynomial? So this should correspond to, let's say P is alpha beta. What object do we associate here? If you think in terms of curves, you will not be able to really get a set up a correspondence. Think in terms of ideals. Now just look at this principal ideal, x minus alpha, y minus beta. And I say that these correspond to each other, and this is not a very easy fact. One side is clear, that if you look at the point P and look at this ideal, every curve in this ideal vanishes, or every, not curve, I should say, every polynomial in this ideal is 0 at P, because it's this, every polynomial in this ideal is, it can be written as something times x minus alpha plus something else times y minus beta, and at alpha beta it is 0. So one way is clear. How about the other way? That is, in order to establish this exact correspondence between these points and ideals, we say, okay, here is this point, here is an ideal which corresponds to this point. I should also say, in order to make this correspondence unique, that there is no other ideal that corresponds to this point. In other words, every polynomial that is 0 on this point lies in this ideal. So this was if you think about it, it's not at all simple to conclude.
I think groups generated by A is the minimal which contains.
It's not quite like that, because here, see, what we are shown is one way, that every polynomial here vanishes at point P. But can there be any other polynomial not in this ideal which vanishes at point P? This requires a theorem to prove, and it's a very famous theorem. It was proved by Hilbert, very famous mathematician. It's called Hilbert's nullstellensatz. This theorem was the beginning of algebraic geometry, because this is what allowed mathematicians to establish this dictionary completely. The theorem says, it has a very general statement, and a more specific statement can be given in terms of this. But okay, let's see. So let I be an ideal in this ring, and let's, corresponding to ideal, you define a set of points P, such that all polynomials A, X, Y in ideal I vanish at P. To collect all such points, and let B, X, Y be in C, X, Y such that take any polynomial b which is also 0 on all points in V. Then there is a power of b that belongs to I. Okay. So this is one connecting. So this rules out what I just asked earlier, that if you start with an ideal which vanishes on a set of points, take any polynomial that also vanishes on that set of points, that polynomial may not necessarily lie in that ideal, but some power of that polynomial lies in that ideal. And this is the best you can say anyway. So this establishes correspondence between ideals and set of points. And now going back using nullstellensatz, we can say that any polynomial that is 0 on point P, some power of that polynomial must belong to this ideal. And since this is a maximal ideal in the ring, this ring, I think we have shown this. This is a maximal ideal in the ring. If I have not shown it, it's easy to show. This is a maximal ideal in the ring. So since the maximal ideal, if power of a polynomial lies in the ideal, then that polynomial or that power of an element lies in the maximal ideal, then that element also lies in the maximal ideal. That's again using maximality we can prove it. So which now putting everything together, we get that this is precisely the set of ideal of all polynomials that are 0 on this point. So this ideal uniquely identifies this point and vice versa. So points correspond to maximal ideals. In fact, we can go further and show every maximal ideal okay. So this also requires some bit of work. So now we have a very nice correspondence. That points correspond to maximal ideals. How about curves? With curves, we have to be a little careful. A curve can simply be union of two lines, for example. That is not, that's a reducible curve. That is, you can factor that curve into two lines. So when I talk about curves, I will talk about irreducible curves, which can't be factored, like circle, ellipse, parabola, they can't be factored further into curves. And again, using nullstellensatz, we can prove that these correspond to prime ideals. The prime ideal corresponding to a curve, if the curve is, let's say, Cxy, it would be okay, and it can be shown that the curve is irreducible if and only if the ideal is prime. But this is very preliminary, because really what we want to study is curves and points on that curve, the properties of points and various other things on a particular curve. Right now we have all points correspond to maximal ideal, curves corresponding to prime ideal. So let's go further. Points on curve Cxy equal to 0. They correspond to take the quotient ring, quotient with ideal generated by Cxy. Now maximal ideal of this quotient ring correspond to points on this curve, Cxy equal to 0.
When we say curve, then how do we identify the collection of points?
Yeah, you can say it's a, since we already have, we can always write a curve in algebraically, that is y cube equals x square minus 2 or whatever that equation is, right? So that much of an correspondence we already had. But going beyond that, points on that, if that particular curve correspond to maximal ideal of this ring. So if you want to study properties of points of a curve, you just need to study the maximal ideal of this ring. Now, something quite magical happens once we are up to this. If you look, let this is actually called the coordinate ring of curve. We can, this, since C is prime, this quotient ring is an integral domain. You've seen this. Okay. So since it's an integral domain, we can form the field of fractions of any integral domain. You can have a field of fractions. So the field of fractions of this curve is represented as C of C. Okay. Now, with a little bit more work, which is not very difficult, but it requires some bit of algebra. Of course, this field of fractions also has all the maximal ideals there. It's now become a field of fractions, so we have to be a little careful in defining what that maximal ideal looks like here. But all those sets are, because everything, the coordinate ring is a subset of field of fractions. So the maximal ideal also are here. And this also happens to be a Dedekind domain. In fact, this is also a Dedekind domain. So which means that every ideal here can be uniquely factored as product of prime ideals. This is the property of the Dedekind domain. Now, there is one more property it satisfies, that it is also a principal ideal domain, which means that every ideal in this ring is principal, which in turn means that every prime ideal is maximal. So, every ideal therefore in this ring can be written as a product of maximal ideals. Maximal ideals correspond to prime points. So, if you think of this as a ring of numbers, right, it's just a ring with a lot of nice properties, so you can view them as a ring of numbers. So, the prime numbers in this ring are points of the curve. And since this is a ring, we can do full algebra on the ideals here. That in turn corresponds to doing some kind, not quite algebra there, but certain very interesting operations on points of the curve. Now this correspondence, and then you have this field of fractions associated with it. This is the full arithmetic you can do in this field of fractions. So in this sense, we have associated with a curve a field which is just a collection of numbers of certain kind where full arithmetic is possible, and the arithmetic on this field has some very tight connection with the operation of the curve. And since arithmetic we understand and we can do, like I just earlier mentioned, that we can do arithmetic in a much more nicer way. We have many more tools to do arithmetic. So we can understand that curve and its properties by arithmetic in this field. And that's the key takeaway. And this has indeed resulted in lots of properties of curves which otherwise we would not have been able to prove. A simple example being, let's say two curves of degree, one curve of degree 2, another curve of degree 3. You understand what degree of curve is? The degree of the highest degree term in the curve. In how many points can they intersect at? 6. Why? Okay, we can see a line and a degree 2 curve can intersect in at most 2 points. In fact, a line and degree d curve can intersect in at most d points. That's simple. But higher degree, let's say degree d1 term and degree d1 curve and degree d2 curve, what is the maximum number of points they can intersect in? Maximum d1, d2? No. It is d1 times d2. Take a circle and an ellipse. You can, at max, they can intersect in 4 points. So that is 2, degree 2, degree 2. So that's 4. So that's just an example, but in general, any degree d1 curve and any degree d2 curve, as long as they don't have a factor in common, I mean, both the curves have a line in common, then it's a trivial thing. But otherwise, the maximum number of points they can intersect in is d1 times d2. You can't eliminate a variable. See, if you can eliminate a variable, yes. But the curve could be any arbitrary. It may not allow you to eliminate variables. And that's proven using algebraic geometry. That is, you take out the curve, look at these coordinate rings, and then argue over this. That's a very simple fact. There are many more interesting facts you can prove. They are also very useful in finding out integer solutions of equations. Like one example was y square equals x cube minus 2. We were looking at integer solutions of that. And we saw that you have to go to higher algebraic numbers and find a solution, but that was a very ad hoc way. We can study solutions on families of curves of certain kind by, again, looking at the geometry through the coordinate ring. Okay, so I'll stop here.